In his excellent review on the first day of the session, Peter Banks made the observation that as far as our knowledge of the magnetosphere is concerned, theory is far ahead of experiment. And I'd like to modify the statement slightly by saying that theoretical speculation is far ahead of experiment. And I'd like you to understand my remarks in this sense. In order to explain the very high electron temperatures which have been observed in some regions of the topside high latitude ionosphere, which I have had available due to the kindness of Larry Brace, mainly from ISIS-1 and ISIS-2 data, fairly high heat fluxes are required in order to explain those temperatures. Now, heat input by precipitating particles is an obvious candidate for this mechanism. Now, if you sit down and make some simple calculations using Coulomb interactions, you find that this heat input is orders of magnitude too low. So then you look for something more exotic, like collective interactions due to beam plasma interactions somewhere in the magnetosphere, therefore coupling an energy source in the magnetosphere to the ionosphere. And I did that and made a simple calculation which seems to indicate that we get heat fluxes of about the right order of magnitude that is needed to explain those temperatures. First, let me explain in a simple picture what the mechanism is about. Now, you have in a thermal plasma, of course, a spectrum, a thermal spectrum of oscillations representing all, essentially, all frequencies and directions and so on. Now, the precipitating beam will interact with those oscillations which travel in the same direction as the beam with about the same phase velocity of the beam. As a result of that interaction, you get bunching of beam particles, which then in turn reinforces the wave, and you have essentially a positive feedback mechanism or instability. Now, which would essentially grow indefinitely. Now, this is the first phase, which is a linear phase. Then in the second phase, as these oscillations grow, of course, nonlinear effects take over, which limits the growth of these oscillations. And after a certain saturation time, you approach a saturation field spectrum. And, well, that is essentially the mechanism which causes then a transfer of energy from the beam through the oscillation field into the random thermal energy of the plasma. The results, the theoretical results which I present are based on the theory developed by Shapiro, published in Soviet Physics JATP. Let me see. Okay. I felt, by the way, this is a very appropriate pointer for this meeting here. Now, this represents the let me see, the symbols are all of the usual meaning. The subscript B refers to beam particles, the subscript E to the thermal electrons. V sub 0 is the initial velocity of the beam particles, and this then represents the density of energy loss of the beam particles. The E sub K are the Fourier transforms of the oscillation field, and this, of course, is a change, an increase in the internal energy of the plasma. As you can see, that the energy lost by the beam is divided about 50% between the internal energy of the plasma and the electrostatic oscillations. This term represents a spreading in the beam energy spectrum, since I forgot to mention that one of the assumptions is an initially monoenergetic beam, therefore the beam has zero temperature initially, and will then wind up with a energy spread. This is essentially negligible compared to these because, at least for ionospheric situations, the ratio of beam density to plasma density is orders of magnitude below 1. However, this effect cannot be neglected because it's partly the spreading of the beam which modifies the interaction, which then results in the establishment of saturation. Okay. Now, what Shapiro did, he represented an approximate solution of the coupled one-dimensional Vlasov and Poisson equations after Fourier transforming both equations. I forgot to say one other thing, incidentally. Because of the very low density of the beam, the nonlinearities develop mainly in the beam and not in the plasma. Therefore, it is permissible in an approximate way to treat the plasma throughout linearly and introduce nonlinearities only in the distribution relating to the beam particles. So that's what Shapiro did. And through some very complicated calculations, he obtained, I just put these expressions on here. This is the saturation amplitude, and as you can see, it is strongly dependent to the kinetic energy of the beam particles and the density of the beam. The saturation time, that is the time in which saturation occurs, is given by this expression, which is essentially inversely proportional to both plasma density and, inversely proportional to beam density, to this power here, and of course, omega sub p is the plasma density, plasma frequency, which is proportional to the square root of the plasma density, so that you wind up with a positive power of plasma density. I don't want to spend too much time on these. The point is that we are interested really in the downward heat flux caused by this heat input. The exact heat flux obviously would have to be obtained by solving the whole problem, continuity, momentum, and energy equations, and then getting the heat flux in the usual way in terms of temperature and temperature gradient. However, we can get an order of magnitude estimate of the heat flux without actually solving the problem if we assume that after saturation has been achieved, the system will be in a steady state. And using that assumption, one obtains the following heat fluxes for these energies of the initial monoenergetic incident beam and these values of the flux density of the precipitating beam and these densities of the ambient electrons. These values are typical from, for example, from ISIS 2 soft particle spectrometer data, for which I'm grateful to Dave Winningham for having me use quite a bit of his data. Now, as you can see, the heat fluxes, first let me say that the precipitating flux is relatively insensitive to ambient electron density. For the same incident energy and the same precipitating flux intensity, the heat flux caused is essentially the same if you keep in mind that this is an order of magnitude calculation. However, the precipitating flux is very strongly dependent on the energy of the precipitating particles and even more strongly on the intensity of the precipitating flux. And particularly the higher fluxes are sufficient to explain the temperatures that have been observed. Now, besides the obvious effect of this heat input on the thermal structure of the ionosphere, it has also a very strong influence on the dynamics. This has been shown in a recent paper by Hartle and Barnes for the case of the solar wind. They have solved the continuity, momentum, and energy equations for electrons and protons for boundary conditions at the base of the solar atmosphere. And in the proton energy equation, they used a parameterized heat input function to simulate some non-thermal heat input mechanism. The next slide shows their results. Now, this is the heat input. This figure is directly from their paper, which is referenced here. This is the heat input function which they used. R sub s is the solar radius. A is the, this is obviously a Gaussian heat input function. A is the location of the center of the heat input in units of R sub s. B is the width. D naught is the strength of the function. N is the density of protons at the point R, and N sub 0 the boundary value at the base of the solar atmosphere. This is a plot of square root of proton temperature at 1 AU, at the Earth orbit, versus this is here solar wind speed in kilometers per second. And the calculations have been performed for a constant width, but with the location parameterized. Now you see that the closer the heat input takes place to the sun, the smaller A is, the more, and the calculation, I should say, is one where they started with D sub 0 equal to 0 and then increased D sub 0, and then the solution point moves along the curve for appropriate A. So as you put heat in very close to the sun, it results in considerable acceleration. As you get further away from the sun, the heat input causes hardly any change in velocity, but instead tremendous heating. Now, this is actually very analogous to neutral gases. If you remember your gas dynamics, if you have neutral gas flow with a critical point, and you add heat input in the subsonic region, it results essentially in explosion. The acceleration is even greater, and the m equals 1, the transition is reached earlier. If you add heat, however, in the region of supersonic, beyond the critical point, then the effect of heat input is actually to throttle the flow and possibly even prevent supersonic transition to the critical point. Okay, in conclusion, then I would like to say that the addition of heat to the atmosphere, to the ionospheric plasma at very high altitudes, and has, in addition to the obvious effect on the temperature profile, is expected to have a strong effect on the dynamics, and including some possible implications on the polar wind. Thank you.
If I understand you correctly, essentially the theory where the waves near the beam phase velocity are transferred to, well, down to lower phase velocities purely by quasi-linear theory.
Yeah, I want to add one thing, incidentally, that I was not aware of the theory of Papadopoulos. Furthermore, it has not really appeared anyway in any reviewed journal. So, but I talked to him in San Francisco at the AGU in December. Using his mechanism would actually make this effect even more drastic, because for the rest of the audience, the explanation, the thing is that there are also oscillations in the ion component, and these oscillations serve sort of as a catalyst to transfer energy from the high phase velocity waves, plasma waves, to very low phase velocities near the thermal velocity. And therefore, of course, they would interact much more efficiently with the thermal plasma than the high phase velocity ones.
Well, also, if you go to this mechanism to completion, to saturation, you wouldn't see the bump in the beam, though. It would be flattened, just by quasi-linear flattening.
No, at least not according to the figure in Shapiro's paper. Here, in the saturation, he has essentially a horizontal distribution, a raised tail, essentially, but which sort of eliminates the bump.
Yeah, he doesn't have the bump.
Yeah, I mean, after saturation is achieved. The bump is there initially.
Correct, after saturation.
And furthermore, I might add that in all of the curves that I have seen from the soft particle spectrometer of Heikkila and Winningham, I have never seen a bump with a positive slope. All I see are plateaus. In fact, I'm in the process now of actually analyzing the data and fitting them to a mathematical function expressing a flow with a spread. I mean, a precipitating beam with an energy spread, and that I think will help me also to better understand what really the spectrum is of the beam. I presume that at the time when the satellite intercepts the beam, that is way below where these interactions take place. So that will be the saturation regime.
Yeah, let me see if I just understand what you two are saying. What you're talking about is electron Landau damping on the Langmuir wave associated with the beam, and you're talking about decay, three-wave decay between the beam and down to the ions. No, so you'd predict heating of the ions, and you'd predict heating of the electrons for the same beam waves.
No, it's also electron in both cases. Also, I'm not talking of Landau damping. That's a linear effect. That's strict.
No, but you have a linear effect in the plasma. I'm talking about the Landau damping of the plasma electrons due to these Langmuir waves. I mean, that's just what I understand. Is that right?
Maybe.
On the three-wave effect, you get the electron plasma oscillations at phase velocities in the tail of the ambient plasma, and they are Landau damped and they draw out the tails. But they maintain the integrity of the beam. His theory would not maintain the integrity of the beam. They would not produce the results of Reasoner and Chappell.
I don't see any Landau damping in your model. Isn't it just coupling down to the ions through low frequency waves?
No, there are two waves. There are ion fluctuations and electron.
Waves.
Yeah, there are two waves that are being pumped by the the pump.
Sure.
There's a pump wave.
There's a pump.
And there's the ion density fluctuations which do nothing to the main body of the electrons.
Yeah.
There's electron plasma oscillations with phase velocities that are less than the beam phase velocity, lie in the region between the ambient
But
plasma.
not much less, because you're supposed to, you said you had a very low frequency difference.
No, they are much less. They go into they pull out the tails. The tail is being formed by
Excuse me,
land
why
out
don't
damping
we
in those
carry on
waves.
private conversations later? Maybe there's somebody else who has a question.
That's all I have for questions.
I would also like to point out that if one could heat the electrons relative to the ions sufficiently, and as I recall, the ratios are like in the 5 to 10 range, then the Kendall and Kendall current-driven instabilities can move down. Whereas normally for unity ratios, the instabilities don't touch off until about the 1,000 kilometer to 1,500 kilometer range. If you're able to heat the electrons down low, say in the 300 to 500 kilometer range relative to the ions, and you can touch off the instabilities at lower altitudes.
Well, that is possible, but what I am talking about really happens much higher. I mean, simply because the data I was using, ISIS 1 and 2, were taken between about 1,000 and 3,000 kilometers. So, and with a downward heat flux, with temperature gradients of 1 and even 2 degrees per kilometer. So, and furthermore, of course, that's actually one of the questions that I would like to see the conference discuss at some time. Whatever the mechanism is for injecting or accelerating these particles in the various regions, like cusp, auroral, and so on, of course, also happens at considerably higher altitude. So you establish your instabilities there. Now, what you are saying is that as a result of the temperature increase of the electrons, then you could also have additional instabilities further down below and heating.
Exactly, essentially a two-step process.
Okay, it's possible.
Leading to a possible mechanism for formation of electric fields down in the 2 to say 500 kilometer region.
Yeah.
That forest motion